All right, hello everybody. In this video, we are going to continue on with our discussion of shear stress or average shear stress. In this case, we're going to be looking at connectors, and how these connectors are actually fastening things together will determine how we do our analysis. So for the first type of connector, what we're going to look at is the case of single shear. This can also be called lap shear. So a single shear or lap shear, I'm going to do my best to draw a little loading scenario here. So what I have are these two plates overlapping one another and some kind of pin in here. In this case, we're going to say that this is a 1/4 inch pin that's holding these two pieces together, and we're going to pull it in tension with 200 pounds. Force on here so we can actually use real numbers. And we're interested in this pin itself and what kind of shear stress is on that pin. So if we were to do a blow up of this pin separately and we thought about what's going on here, what we would see is that there's, like, in essence, a plane that it would shear at. You know, if you think about after it fails, I end up with two separate pieces, a top piece and a lower piece, and I end up with this single shear plane. And there is only one of them, and that's why we're calling it a single shear. So going back to our tau is equal to V over A for our average shear stress. Our shearing force would be this 200 pounds, and our sheared area would be the cross-sectional area of the pin, or pi over 4, that's 4, times the diameter of the pin squared, so pi over 4 squared. And that gives me something like 4.07 kips per square inch. If I were to take the same type of scenario, but instead of having the single board up top, I had more like a pinching situation, something like this. And we're still going to have the same 1/4 inch pin. I think I'm supposed to draw that more oblong, but you get the idea, 1/4 inch pin. And this, we're going to still be supporting the same 200 pound tensile load here. So if we were to look at this pin, what I can see is now this whole board, if it failed, would be pulled straight out, and I'd end up with two sheared areas, or three pieces of this pin as it fails. So something a little bit like that for my sheared areas. Hopefully you can see how this board is pulling on it on those two sides, and you'd end up with this little chunk in the middle popping out. So because we have two shear planes, two stressed sections, I'll say two shear planes, that's what I did up above. This will be called double shear. As far as our shear stress, it's pretty easy. All we're doing is we're increasing our area by 2, so we have the same 200 pound load. But now, since we have two of these areas, each one having an area of pi over 4 times this 1/4 inch squared, gives me a stress of exactly half what I had before, which we'd expect of 2.04 KSI. And you can imagine that you could have as many planes as you can if you were to create almost like a hinge looking structure, and then look at the pin there as well. So there's single shear, double shear. The other type of situation we need to look at is shear rupture. So shear rupture looks at the material strength of our board as opposed to the pin strength. So for instance, if this pin were strong enough but the pin were set too close to the front of the board, you can imagine this big chunk of material being pulled out and the top board failing. So that in essence is what shear rupture is. So let's take a look at one board and how that would look. So if we were to pull at the same 200 pounds we were just looking at before, so what I can imagine is if I had the same pin, what I'd end up with are two failure planes because I have this chunk of material that's left over. So I'm going to try and do my best to draw these two planes. This is going to be kind of crazy in the 3D looking thing, but I'd have one plane along here, one plane back there. I think a better way to look at this would be in a 2D context. So let's say from a top view, probably should have started with this top view. If I have this pin and I can think of this material being ripped out from the edge on over, and if we were to say that this board were a 1/4 inch thick, and our pin were placed back from the edge a total of 0.5 inches, then I can see that the area from this green area and this blue area end up with two shear planes, each shear plane having a cross-sectional area of 1/2 inch by 1/4 inch. So the total area that must be sheared would be two sides, the blue and the green side, each side being a 1/4 inch by 1/2 inch back. And that gives me 0.25 square inches. So when we talk about our shear stress on this board, our V over A, our shearing force is still this 200 pounds. And I'm dividing by this total area 0.25 inches squared, leaving me with 800 pounds per square inch for a shearing force on this material, on this board. So, and of course you could do that for the top plate as well, and you'd have double shear. So for instance, if I were looking where I drew this guy up here, I'd have a plane there, I'd have a plane down there, and end up with a whole bunch of planes. Actually, I'd end up with 4 planes to be exact. And you can look at the material of the board in that aspect as well. So that's the design of connectors with shear rupture and with single shear and double shear. So good luck, and I look forward to talking to you soon. Thanks.